Hello students, this is the third session of group theory class. In the previous class, we had seen some results on normal subgroups and also definition of quotient group. So let us recall the definition of quotient group again. A group G by H, we denote the quotient group as G by H of all cosets. You're combining all the cosets of the normal subgroup H of G and then putting it into one set, and you call that as a quotient set. And since that forms a group under binary composition, HA, HB is equal to HAB. So we call this as a quotient group. Under the binary composition, HA, HB is equal to HAB. Then if suppose G is abelian, then the factor group G by H will also be an abelian group. As I had given an example in the previous class, I had taken Z6 and explained how the quotient group forms. So in that case, Z6 is an abelian group. So even G by H will also be an abelian group. So you can just see that example and you'll understand it better. If suppose the operation on G by H is addition, then we write HA as H plus A plus H plus B, that is equal to H plus A plus B. That is how we denote in case if it is addition. In case if it is any other operation, we denote it by star. So let us look at the theorem now. If H is normal subgroup of a finite group G, then order of G by H is equal to order of G divided by order of H. So the proof is, by definition we have order of G by H is nothing but number of distinct cosets of H, and number of distinct cosets of H is nothing but index of H in G, and index of H is given as order of G by order of H, that is by Lagrange's theorem. Lagrange's theorem you would have already studied in the previous semester. Lagrange's theorem states that order of any subgroup divides the order of the group. So we have index of H and G is equal to order of G divided by order of H, and that will be the order of G by H. So in the example which I had given earlier, Z6, order of Z6 is 6 and order of H is 2. So we get order of G by H is equal to 6 by 2, that is equal to 3. So you get 3 elements in the set G by H. Now let us look at one of the example problems. If a cyclic subgroup N of G is normal in G, then every subgroup of N is normal in G. So we have a subgroup N which is cyclic and normal to G, and you take any other subgroup of N, say H, that will also be normal in G. So this every subgroup of N is will be normal in G. So for that, we know that the subgroup N is a cyclic subgroup. So I take, let A be the generator of a cyclic and normal subgroup N of a group G. Let H be a subgroup of N. Now every subgroup of a cyclic group will also be cyclic. I take, let M be the least positive integer such that A power M belongs to H, and I take H to be a cyclic subgroup generated by A to the power M, because every subgroup of a cyclic group is also cyclic. Now we need to show that H is normal in G. That is to show that G inverse belongs to H for every H in H and G in G. If we show that, we can say that H is normal in G. So for that, I take an element H belonging to H. Then H is equal to, since H is a cyclic group, I can write H is equal to A, and generator is A to the power M. I'll write H is equal to A to the power M whole to the power K for some integer K. Thus, for all G belonging to G, we have G inverse can be written as G A to the power M whole power K into G inverse, or I can write this as G A power K G inverse whole to the power M. The reason is G inverse whole to the power M is equal to G A to the power M G inverse. This we have already proved in the previous class. In case you need any clarification regarding this, you can just text me for this clarification or look into some other textbooks. Since n is normal and a to the power k is an element of n, so here n is a normal subgroup and it is a cyclic subgroup generated by A. So any multiple of A will be an element of n. For that reason, a to the power k also is an element of n, and n is a normal subgroup. So we can say that G A power k G inverse belongs to n. So this implies G A power k G inverse is equal to a to the power p. The reason being n is a cyclic subgroup for some integer p. Now GH, we need to check whether GH G inverse belongs to H or not. So we consider GH G inverse, that is equal to GH G inverse is nothing but G A power k G inverse whole to the power m. So I can write this as GH G inverse is equal to, this is A power p whole to the power m, or I can write this as a to the power m whole to the power p. Now this is an element of H. Since H is the subgroup generated by a power m, so a power m whole to the power p also belongs to H. Therefore H is normal in G. So we can conclude saying that every subgroup of n is normal in G. If it is normal and cyclic, then every subgroup will be normal in G. Now let us look at the next important topic, that is homomorphism of groups. Now you take two groups here, that is G and G dash, where in case of G, in the group G, the operation is circle I take, and in case of G dash, the operation is star. Now we have a mapping F from G to G dash is said to be a homomorphism of the group G into the group G dash if this condition holds good, that is f of A circle B is equal to f of A star f of B for all A comma B belonging to G. Now say you have f from G to G dash, and you have this set as G comma circle and this as G dash comma star. Now we have a mapping. So when I have a mapping, A is mapped to f of A, B is mapped to f of B, and we take the operation A circle B. When I say take A circle B and I assign it to be C here. Now we are checking whether the C is mapped to f of A star f of B. If this holds good, that is C is mapped to f of A star f of B, then we say that F is a homomorphism. Here the operation should be circle, whereas here the operation should be star. If this holds good, then we say that F is a homomorphism. And if this function, if this mapping F is 1, 1, then we call that kind of homomorphism as monomorphism. And if this F is onto, it is called as an epimorphism. In the next classes, I will tell you how to check whether F is 1, 1 or onto. Now let me tell you give you some examples of what is homomorphism. You would have two groups, G comma circle and G dash comma star. Then you have a mapping F from G to G dash given by f of x is equal to E dash for all x belonging to G, where E dash is the identity of G dash. This means that all the elements of G are mapped to the identity element of G dash. So we have f of A is equal to E dash and f of B is also equal to E dash. So f of A circle B is also an element of G. So f of A circle B will also be mapped to E dash because every element is mapping to E dash. Say you're taking all these elements mapping to only single element identity. So we have f of A circle B is equal to f of A star B. This implies E dash, f of A circle B is nothing but E dash, and f of A is E dash, f of B is also E dash, which is nothing but E dash is equal to E dash. So the left hand side is equal to the right hand side. So we say that F is a homomorphism. So let us look at one more example. If you have a G to be a group and there is an identity map, that is I from G to G itself, defined by the mapping is you're mapping the elements to itself. So A is mapped to A, B is mapped to B, C is mapped to C, like that. So it is defined by I of G is equal to G for all G belonging to G. This is a homomorphism for the reason that I of A comma AB is equal to AB, because AB is mapped to AB, and A can be written as IA and B can be written as IB. So we have IAB is equal to IA IB. Since the operation is the same, since it is group to itself, this is a homomorphism. The third example, you have two groups. The first one is, it's a group of integers, and the second group G dash I denoted by 2 to the power n, where n belongs to Z, is a group with respect to multiplication. Here it is addition, here it is multiplication. Now I take a mapping f from G to G dash, defined by f of n is equal to 2 to the power n for all n belonging to Z. Now I need to check that whether this is a homomorphism or not. For that, I take two elements of G, n1 comma n2 belongs to G, and then I take f of n1 plus n2. So this is equal to, by the definition we have, f of n1 plus n2 is equal to 2 to the power n1 plus n2, and this is equal to, by law of indices, I can write this as 2 to the power n1 into 2 to the power n2, and we know that 2 power n1 is nothing but f of n1 and 2 power n2 is nothing but f of n2 by the definition. So we have f of n1 plus n2 is equal to f of n1 into f of n2. Here you have addition for G, whereas for G dash you have multiplication. So therefore we can conclude saying that f is a homomorphism. Now let us look at some of the properties of homomorphisms. So theorem 1, let f from G to G dash be a homomorphism from the group G comma circle into the group G dash comma star, then f of E is equal to E dash, where E and E dash are the identity elements of the groups G and G dash respectively, and f of A inverse is equal to f of A the whole inverse for all A belonging to G. That means identity is always mapped to an identity element. Whenever you take a homomorphism, identity is always mapped to identity, and f of A inverse is nothing but f of A the whole inverse. So to prove that, we have by data that f is a homomorphism. Since f is a homomorphism, for all A comma B belonging to G, we have f of A circle B is equal to f of A star f of B. Now f of A star E dash is equal to f of A, because f of A into E dash, it is a group, so anything multiplied with an identity element, you get back the same element, and this f of A can be written as f of A circle E, and this is equal to f of A star f of E. The reason is f is a homomorphism. So we have f of A star E dash is equal to f of A star f of E. By left cancellation law, we get that f of E is equal to E dash. So always remember that the identity element is always mapped to an identity element of the other group in case of homomorphism. Now consider f of A star f of A inverse. Since f is a homomorphism, I can write this as f of A circle A inverse, because of the groups G and G dash. This is equal to A circle A inverse is nothing but E, because this is a circle operation in the group G. A circle A inverse is equal to E, so f of E is equal to E dash from the previous result. Again, we have f of A inverse star f of A is equal to, under the same argument, this is also equal to E dash. So we have f of A circle star f of A star A inverse is equal to f of A inverse star f of A, which is equal to identity. So this means that one is the inverse of the other. So therefore, f of A inverse is equal to inverse of f of A, or I can write this as f of A whole to the power minus 1. Now we'll go for the next theorem. If f from G to G dash is a homomorphism, then the set f of G, that is equal to f of g for all g belonging to G is a subgroup of G dash, is a subgroup of G dash, where f of g is called the homomorphic image of G in G dash. So here, if we have this f of g as set of all the images of G of G belonging to G, this is called as the homomorphic image. Now we need to show that this f of g is a subgroup of G dash. See, G and G dash, G dash can be a bigger set compared to G. So you're mapping all the elements of G to another element of G dash. Just hold on. Wait, I'll just explain this. Say you have a set G, and here you have a set G dash. Now, this you have elements A, this is element B, and this is element C, and this is element D, sorry. And these are mapped to an element f of A, f of B, f of C, f of D, and you may have some other elements here, say 1, 2, and so on. So these images are called as f of G. So you're mapping A to these are called, these are the elements f of G, and you may have some other elements within G dash. You're showing that f of G is a subgroup of G dash. Okay. Now, so we need to prove that f of G is a subgroup of G dash. For that, to show, we have f of G is equal to f of G for all G belonging to G. To show f of G is subgroup of G dash. Whenever we need to show it is a subgroup, we take two elements A comma B belonging to G. We show that A B inverse belongs to G. Similarly, we have x dash y dash belonging to f of G. We show that x dash y dash whole inverse belongs to f of G. So since x dash y dash belongs to f of G, there exists x comma y belonging to G such that f of x is equal to x dash and f of y is equal to y dash, because you have a mapping f of G. You have a mapping here. So whenever you have x dash y dash in f of G, there will exist x and y in G such that f of x is equal to x dash and f of y is equal to y dash. Now you consider x dash y dash whole inverse, that is equal to x dash is equal to f of x and y dash is f of y the whole inverse. This is equal to f of x into, by the previous result we have f of y whole inverse is nothing but f of y inverse, and since f is a homomorphism, we have this as f of xy inverse. This belongs to f of G, as xy inverse is an element of G. So this will be an element of f of G. Hence, we showed that x dash y dash whole inverse belongs to f of G. So f of G is a subgroup of G dash. Now, the third and the fourth theorem is left to an exercise. Here, you need to show that if f from G to G dash is a homomorphism and H is a subgroup of G, then f of H is also a subgroup of G dash. Under the same argument, in place of G, you replace it as H. You get back the same result. Similarly, also you can prove that homomorphic image of an abelian group is also abelian. Take an abelian group and take the image of it and you show that it is also an abelian group. These two are left as an exercise. This is a very small theorem. You can prove it in 3 lines. In case of any difficulties, comment on this video. I will explain it. Next, theorem 5. If f from G to G is a homomorphism from the group G into itself and H is a cyclic subgroup of G, then f of H is again a cyclic subgroup of G. H is a subgroup, cyclic subgroup, and if f is homomorphism, then f of H is also a cyclic subgroup of G. So by data, H is a cyclic subgroup of G, and from the theorem 3, we have already showed that f of H is a subgroup of G. Only remaining thing what we have to prove is f of H is cyclic. So to show that, I consider an element x belonging to f of H, then there exists y belonging to H such that f of y is equal to x. Since x belongs to f of H, there will be a y in H such that f of y is equal to x. Since y belongs to H, and y belongs to H means H is cyclic already. We know that, and it is generated by A. So y can be written as a to the power m, where m belongs to z. So therefore, I can write x is equal to f of y, that is equal to f of a to the power m. Now we have two cases, that is m can be a positive integer and m can be a negative integer. So case 1, let m be positive integer. So x is equal to f of a to the power m. So this implies x is equal to f of a to the power m is nothing but a into a m times. And this can be written as, since f is a homomorphism, I can write it as f of a into f of a into f of a m times. So this gives x is equal to f of a whole to the power m. Next, second case, let m be negative integer. So when m is a negative integer, I can write m is equal to minus n, where n is positive integer. So we get m to be a negative integer. X is equal to f of a to the power m, that is equal to f of a to the power minus n, or I can write this as f of a to the power minus 1 whole to the power n. From the previous result, I can write this as f of a inverse whole to the power n, or from the theorem 1, I can write this as f of a whole to the power minus n, and that is equal to f of a whole to the power n. Again, in both the cases, we have got that x is generated by f of a. So this shows that f of a generates f of h. So taking any element of f of h, we have showed that that element is generated by f of a. Hence, we can conclude saying that f of h is a cyclic subgroup of G generated by f of a. So this is all for today's class. In the next classes, I'll be teaching about kernel of a homomorphism, some theorems, and go to isomorphism, which is very important in group theory as well as in the higher studies of group theory as well. Thank you.